Hello, this is GAT7, and today we're actually going to start learning a bit of assembly here and the general basics of it. Alright, so let's get started. So let's say we have a processor here, and over here we have a bunch of instructions. What this processor is going to do is read one instruction, process it, do whatever it says, read the next one, does that, then it's going to read the next one. Does that, except one thing. How does the processor know where to read the instruction from? So let's call this address where the instruction is here 0x60 for whatever reason. Let's just say it's at 0x60. So what we're actually going to have here is something called a register. And this one is going to be a program counter, or for short, it's going to be called PC. Now, what a register is, just kind of think about it as a general term of storage. So let's say we have an 8-bit register. That means we can hold 1 byte. If we have a 16-bit register, we can hold a 16-bit value in there. 32-bit, 32-bit, 64-bit, 64-bit value. In general, if we have a 8-bit processor, that means the instruction that it's given is going to be 8 bits. It's going to be the bit amount of a processor generally refers to the instructions it can receive and how many bytes each instruction is, or bits. So again, to the program counter example, let's say it starts at 0x60 here. So it's going to read that value, increment it by 1. So it's going to be 0x61. So then it's going to read this one, do what it says, and then increment. That's basically the general pattern of how a processor reads instructions. So it comes from the first memory address, and then it increases the ROM or RAM address, depending on where your code is. So right now, I'm going to erase that, and I'm going to start with a simple assembly language, in my opinion. And what this is 65C816. Despite having a complex looking name, here I'll make you feel better by breaking it down right now. It's generally easy. So 65 means it's part of the 6502 family. C means CMOS. 816 means that registers. It can rather be 8 or 16-bit. So don't you feel special now, because you know what that means. Let's actually see some things on how it works. In an assembly language, you generally have instructions that are kind of like mnemonics. So like store and load. Store and load are the two things I'm going to teach you today. And an assembly program can actually be written kind of like a grammatical sentence. If you were to read an instruction correctly, it would actually make sense in English. We're going to shorten those. So we're going to shorten load to LD. We're going to shorten store to ST. But what will we be loading and storing? Well, 65C816 has multiple registers like PC, the program counter from earlier, but other things like SP, stack pointer, and the registers A, X, and Y. Like I brought up earlier, every single processor is going to have a program counter. If not, then it's not going to be able to execute the instructions correctly. But basically, the A stands for accumulator. And these two are what we're going to call the index registers, which will be used for indexing. More on that later, but the accumulator is going to be used for things like math and stuff. So these are the three general registers we're going to work with for 65C816. Again, ARM has a lot more general purpose registers and a lot more registers that do more things. Let's go back to these mnemonics here. So load and store. So what I want to do is use A here and kind of think about it, a register, as a variable, except you don't have infinite variables, you just kind of have these few registers. What you have is what you got. So let's load into A. So if I put load then A, then it's generally assumed then into is in here. And if I hit A here, that's generally going to be store A. Over here in this section is going to be my code, or ROM basically. And over here in this section is going to be my RAM. So in my RAM I'm going to have, let's just say, different cells for each single byte. Let's just call this first one here 0. And let's go from left to right, top to bottom. So 0, 1, 2, 3, 4, 5, 6, 7. And let's just go with that. These will be our memory addresses. And over here, we're just going to store code. So let's get into an example piece of code here. So let's get into a general line of code and break it down. So let's say LDA $0, 0. Well, let's get into what the $sign means here. So we got load into A $0, but what does that mean? If I say I have a $sign, that's going to give me a hexadecimal number, which means that I can say things like 0th or 10, which would be the decimal equivalent of 16. Yeah. Then we also have this percent thing here, which is binary. So if I were giving an 8-bit number, it would generally be like 0000011, and that would be 3. It's going to be a binary number here. Let me just draw a line here to separate that section. But there's one last thing that we're going to use, and this is the hash symbol or pound symbol or whatever you call it. And that's going to be what we call an immediate value. So let's see all of these in example here. Load into A, hexadecimal 0. So since we're not giving it an immediate value, we're going to load into A whatever is into 0. Let's say the number 5 is in memory address 0 here. So in that case, A equals 5. But let's also give another example where we're loading into A immediate hexadecimal 0, 0. In this case, A equals 0. But why is that? Well, immediate means we're loading a value immediately, or right as we say it. So when we're loading into A immediate 0, 0, that means load 0 into A. Don't look into the RAM. But when we don't say immediate, we're going to just look into the memory address. So let me just fill these out with random numbers. I'm just going to write them as decimal for simplicity. 42, 5, 6, 50. Just random numbers here. So let me erase this. Alright, so let's have an example of storing now. So first let me load a value into A. Let's load the value at memory address 02. So how I would do that, if you remember, I would use hexadecimal. Hexadecimal 02. I could use binary, but there'd be no point in that now. We may see usage of that later, but generally you're going to want to use a hexadecimal number. And so now A is going to be equal to 2, because it just so happens that 2 is stored into 2. Now we're going to store A at memory address 05. And what that's going to do is, if we look at memory address 05, 0, 1, 2, 3, 4, 5, this number 42 is not going to be 42 anymore. It's going to be overridden. And instead, now what the value at 05 is going to be is 2, because we loaded A into 2 and we're storing A into the memory address 05. Some people may be like, okay, what if let's store A into memory address 00. But you can't store anything into an immediate. That doesn't make sense. That's bad. You don't do that. To give an equivalent to what this would be like saying, okay, you know the number 7? Yeah, I know the number 7. Well, change it into the number 3. That doesn't make sense. You can't turn the number 7 into the number 3. Like, I guess you could do that, but that's not really a 3. Just take my word for it. You can't change a 7 into a 3. So no using storing into A at an immediate value. It's bad. But what happens if we have a 16-bit value? Because right now we're assuming that we're just using 8-bit values. So what if we had 16-bit? So let me just erase my code here. And so instead of we're going to assume A is going to be 16-bit, and I'm going to load the value whatever's at 00000. And what it's going to be doing is it's going to load the value at 00, but it's actually going to make it so A equals 0x 0305. It's not going to read this as 0503 as you might expect, because the SNES is going to be in little endian. Now, if it were big endian, then yes, it would read it as 0503. I know I said that those were going to be decimal before, but let's just assume they're hexadecimal now. Either way, 5 and 3 in hexadecimals have the same meaning, so it doesn't really mean much. Now, if I were to store a value at little endian, let's just change this into a constant now. So let's just load into A the constant 0. And now I'm going to store it, no, not 0, 01. And now I'm going to store it at memory address 0000. And what's going to happen is this, like I said earlier, is going to be 0100. So it's going to write to it different backwards. It's not going to write it as 0001. Instead, it's going to be 0100 in the RAM. And if I were to load the value at 0000, it's going to load it as 0001. So everything is going to turn out okay if you don't mess with those in 8-bit mode or whatever. They're going to be fine generally. Now I've been using A as all my examples just because you're going to generally want to use A, but you can use X and Y if you want. So that's basically how you would read and write values in different modes to the RAM and such. Now I'm just going to give one last piece of advice. The semicolon in an assembler generally means you have a comment, which is good because it's a lot of times you're not going to remember what your code does. So commenting is a good way to remember what that section of code does. So if I had load a blah blah blah, I can comment here that it's loading the power up status or whatever. So hopefully you've learned something here. You've learned two main 65C816 instructions, load and store. And there's just one last thing I want to say. Sometimes you're going to want to write the 0 value to a place. So like, let's say I want to zero out the value at 02. Again, I'm going to assume we're in 8-bit mode here. I can just hit STZ. And what this generally stands for is store 0. So I'm going to point it to memory address 02. Or since it's hexadecimal, 0x02. And now this 2 is going to become 0. Hope you enjoyed this tutorial, and I'll see you all later.